Okay, that looks like it's working. Okay, so so let's pick up where correction. Let's start with a whole new thing, right? So y'all recall we kind of skipped chapter 4 when one would have expected we would have done it, because it's the only nice, cleanly defined chunk of the course that isn't really kind of prerequisite to chapter 6 and 7. So it's the only thing that I can delay, and so I do. Anyway, with that in mind, we're going to go back and do it now. Now we've got chapter 6 and 7 mostly done, pretty much done. Done. But if time permits, I might go back if we have the time and do some more of those examples, those supplementary examples. Okay, so section 4.1, really short discussion. Most of what's in section 4.1 is old news. It's single variable calculus, talking about Taylor series and stuff like that. That is, of course, in the prerequisite trail for this course. I'm going to assume that you're good to go on Taylor series. So let me just remind you, though, Taylor polynomial, this is the formula for the degree K Taylor polynomial for an appropriately regular single variable function. So I hope you all recognize this formula. And it's a great big monstrosity, so why on earth would we write down this great big monstrosity? What makes that useful? And the answer, there's different ways to say this, of course. My favorite way to say this is that this is the unique polynomial of degree K that mimics the function. Really, to put it, briefly, right? This is the only polynomial of degree K that copies f in the following senses. It has the same value as f. It has the same derivative as f at the point A where you're basing your approximation. Same value, same derivative, same second derivative, third derivative, fourth derivative, etc., all the way up to kth derivative. So for single variable functions that are appropriately regular, there will always be exactly one such polynomial, and this is it. So that's a take on why we care about Taylor polynomials. Okay, they have the advantages of being polynomials, and that makes them easy to deal with, and yet they're pretty much copycatting the function. And so if you're interested in some function, the Taylor polynomial is a way to kind of get your hands on the function but get all the advantages of dealing with a polynomial. Okay, so let's talk about the same thing in a multivariable setting. Same basic idea. The Taylor polynomial of degree K is the unique polynomial that mimics the function. A unique polynomial of degree K that mimics the function in the same kind of analogous kind of way. So that means at the point where you're doing the approximation, this polynomial has the same value as f at that point. It has the same derivative. Wait a minute, can we say derivative? There's a bunch of partial derivatives. Okay, so it has all of the same partial derivatives. And this you could lump into a single statement. You could say it has the same derivative matrix. That's sure, fine. But I'm going to say it has all the same partial derivatives. And then et cetera, et cetera. It also has all of the same higher order partials up to order K. Okay, so again, it's just an attempt to mimic a function f as much as possible in terms of values and derivatives up to the kth order, and there will always be a unique polynomial that will do this. Now, how you write down that polynomial is a little notation heavy and clunky, and not something that we're going to need in this class. It's in the book, and you're welcome to look at that if you're interested. I'm going to show you how to write down just the degree 2 Taylor polynomial, and this is enough, both in terms of what we need and in terms of heavy, sort of notational inconvenience. So here it is. This is the formula for the degree 2 Taylor polynomial. Some of this you're going to notice is pretty straightforward. Obviously, we start off with f of a. I say obviously, but Unsurprisingly, we start off with f of a. Also unsurprising, notice that the 0th and first order terms, pretty familiar. That's the linear approximation. How about that? That's convenient. And so to make it second order, we just need to add in the second order term. It turns out that this is what it is. In particular, this is what it is, with the understanding that this thing here is this thing called the Hessian matrix. And it's the matrix of second partials of the function. So this is what works out. It's a little bit hard to just at a glance see this coming, but that's not hard to confirm. And so I encourage you all to do this, right? In the same way, using morally equivalent methods to how you would confirm that this Taylor polynomial here has all the right values and derivatives. Just do the same thing here. Take this expression, write down its partials, write down the second partials. Notice that they'll all be what they're supposed to be. Okay. All right. So there you go. Real quick, while I'm here, I'll notice you may recognize this expression. Perhaps it'll be more recognizable without the 1/2 there. This is something that you all saw in linear algebra. It's called a quadratic form. And this is one of the reasons why quadratic forms are interesting. There's a lot of reasons, right? But this is a pretty good one. Quadratic forms are a really important part of how you understand Taylor polynomials. And we're going to make some pretty nice and natural use of this formula in just a few minutes, actually. Okay. All right. Okay. Okay, so that was 4.1. There's, again, a bunch of stuff I'm leaving for y'all to read because it's mostly review. But make sure you read through all that. Make sure you're good with all the rest of it. Okay, let's do 4.2. So extrema. I'm going to start with a flashback to single variable calculus. I hope this looks familiar. Let's see. I guess I can do it like that. So here's a single variable function, and I've deliberately drawn a carefully constructed graph here of a single variable function. I don't want to get bogged down in the algebra, so I'm not going to write down the formula or anything like that. But notice it's got a little bit of everything. It's got some sort of level spots, and it's got a point where it's not differentiable, and etc. Okay, so that is our function, and let's think about what is our process for how we find the maximum value of the function. Right? It's very important to be able to maximize functions. Functions could represent things that we're interested in. Sometimes we want to make those as big as possible. Right? So here's a point of view. As you all know, I like to take points of view that are most conveniently adaptable to our new setting so that you can see how we're really doing kind of the same thing in the multivariable context. So this might not be exactly how you saw it, but this is, I think, pretty close probably to what you've seen. So here's my take. These three conditions right here allow us to do something. If we know that a point is in the interior, and if we know that the function is differentiable at that point, and if we know that that derivative is not 0. Now notice this point here. Right, I'm going to call that point x. That point x satisfies this condition. If you were to take this drawing that I've made and sort of interpret it as intended, I've tried to make it look like that's, nice and smooth right there. So let's take that. This is differentiable. So that point is in the interior, right? It's not a boundary point. It's not on the end. Again, as per the suggestion of the drawing, we're going to take this as a differentiable point. And what is the derivative? Well, the derivative is negative something. Looks like about -2. So not 0. And I claim that whenever this trio of conditions happens, we can instantly conclude that means the function is in the process of increasing one way or the other. Now, it doesn't look like it's increasing. It looks like it's decreasing. Certainly as x increases, the function decreases, right? But if I were to go to the left from the point x, as I go to the left, the function is increasing. Right? So adapt appropriately to the circumstance, but one way or the other, in this case left, one way or the other, though, the function is increasing. And then I argue, and I think this is a pretty easy claim to believe, if the function is in the process of increasing, you're not at the maximizer. That couldn't possibly be the maximizer you're looking for. It's still going up. So, as I go to the left, anyway, in this case. Everybody buy that? Okay. All right. So, how do we use this in practice? Do we go through and enumerate every single point in the entire interior and just check them one at a time? Well, no, we couldn't possibly, right? There's way too many points. We can't check all of them. So what I'm going to do is take advantage of the fact that, frankly, the vast majority of points in the domain, this is going to be true. And rather than confirming directly, I'm just going to hunt for the very few points where this is not true. And those are the points that I have to worry about, right? So if we find points that are not in the interior, right, the boundary points in particular, they're not in the interior. Okay, well, my argument fails here. I can't just say, oh, well, the other two conditions are satisfied, and so I eliminate these points as possible maxes. Take this one here, for example. If I look at this left endpoint, is there any direction from that left endpoint A in which the function is increasing? There's not. It would have if I had space to the left to go, but I don't have any space to the left that I can continue to go. So that, being an interior point is necessary for this argument to actually hold water. Okay, let's see here. And likewise, if there's a point where the function fails to be differentiable, such as that point, right? The function's clearly, the clear suggestion of how I've drawn this is that the function's not differentiable there. So what are you can't draw conclusions from the derivative if there is no derivative. And then lastly, points where the derivative is 0, like here. Well, I can't use the derivative to conclude that the function's increasing in one way or the other if the derivative that I would try to do that with is 0, and therefore, at least instantaneously, the function's not changing at all in either direction. So if any one of these three things happens, right, notice that these are now ors. Right, if any one of these three things happens, then my argument crashes and burns. I've got nothing. I can't conclude anything about said points. And so it's not, and here's where the misunderstanding happens. A lot of people mistakenly think that if you find a point that satisfies one of these three conditions, then you've found a maximizer, or you've found a minimizer, or it would have to be one or the other. And it doesn't. These are just the points that we can't eliminate. These are the points where we have to confess, I have no idea what's going on there. Right? So we don't get to conclude anything. Now we conceal that failure by giving them a name and calling them, so we're going to call them critical points. And okay, so now I feel like I know something, right? If I find that a point satisfies one of these conditions, well, I know something. I know that it's a critical point. But critical point is code for, I've got no idea what's going on there. That makes sense to everybody? Okay. All right. Okay. And then, of course, now in practice, what we call critical points are, again, the points where our argument fails, and so these are the points where I can't eliminate it. That means it might be the maximizer I'm looking for, and then if I just look at the picture, then very often I can actually conclude, yeah, you know what, I think that one there is the absolute maximizer. Okay. All right, so let's take a multivariable version of this. You'll notice I've laid this out on the page deliberately in very, very similar way. Again, very much on purpose. So here we go. We're looking at a graph. You'll notice I've got a function of two variables. So x and y are my inputs, and then z is my output. So this is a graph. And that being the case, our picture you see we have here, there's various interesting things happening. Again, we're going to take as is suggested by what I've drawn that it's mostly a smooth graph, except for now here's a point where it's noticeably not. Right? But other than that, it's mostly smooth. And again, there's a set of three conditions that I can write down. And if these three things happen, that's definitely not a maximizer. Right? So you take a point like this one right here. At that point, that's in the interior. We're going to take as suggested by the drawing that this is a point where the function's differentiable, and it looks like the gradient's non-zero because it looks like the gradient is, let's see here, the gradient appears, to my eye anyway, to be pointing about like that, I suppose. Something that seems to be the uphill direction. Whatever. Anyway, it's that doesn't look like it's zero. And so again, that point can't possibly be a maximizer. In fact, the function is in the process of increasing, but not one of two different directions that I have to choose from. I have many different directions to choose from, but in particular, at that point, I can go in any direction because it's in the interior. And I know that if I go in the direction of the gradient, the function is increasing because that gradient's non-zero. Okay, and therefore that could not possibly be the maximizer that I'm looking for. So notice it's morally an equivalent argument, right? Same basic idea, just sort of adapted appropriately to a three-dimensional context. Likewise, then, I want to look now at points where any one of those conditions fails. Points on the boundary. Points where the function fails to be differentiable, like there. Points where the gradient fails to be non-zero. Okay, in other words, where the gradient is zero. Like so. And my argument fails. I can't conclude anything. Might be maximums. They might not, right? But they might be. The point is I don't know. So I can't eliminate them, and so I do pull the same little fast when I call them critical points to make it sound like I know something, right? When in fact the whole point to this is that I don't really know anything about what's going on at those points. Okay. All right. Now, do notice that the number of possible classifications much simpler in single variable. There are points that are maxes, that are points that are mins, right? And then there's points that are, I guess you call those inflection points, right? Where it's kind of it's neither max nor min. It's like it's a would-be max as seen on the left side. It's a would-be min as seen on the right side, right? But anyway, pretty much these are the three different scenarios, right? And it's more complicated than that in higher than one dimension. So, for example, you look at this. There's a max, and there you can imagine what a min would look like. I guess I didn't draw one here. But there's also this little weird shape right here, right? And that's what we call a saddle point. So saddle point because it kind of looks like a saddle in the sense that it curves up in the front to keep you from falling forward. It curves up in the back to keep you from falling back. But it slopes downward to the sides because you got to have somewhere to put your legs. Right? So saddle point. And, of course, it's also dated because they had not invented Pringles when this terminology had been settled. So I think these days we would call them Pringle points. Yeah?
That's a unique point. Like in that area, they'll only use one saddle point.
Yeah. Well, no, in this particular picture, there's only one. But no, you could absolutely have multiple saddles.
Well,
Yeah.
I mean, like in the neighborhood of the point, there's only one point, which is the saddle.
Yes. Yeah, that's right. Exactly. Yeah. Yeah, that's right. So the point that is called the saddle point is that particular point where it's curving, where it's both level, right? It's got to be horizontal, tangent plane, and curving as we just described. Yeah. So yeah, just the one point. Okay. Let's see here. Yeah.
Sorry.
Mhm.
For the saddle point,
Yep.
could it be going like the other way? Could it be like an upward saddle, or does it always have to?
It's got to go both ways is the point, right? So this one is it's kind of curving down in one direction, but it's kind of curving up in the other direction.
Okay.
Right? So let me put it this way. If you take a Pringle and you flip it upside down, it still looks like a Pringle.
Okay.
Does that make sense?
Yes.
Yeah. It's different kind of Pringle look, but anyway, still. Yeah. All right. Okay. Now, and it gets weirder than this. Saddle is not our only sort of new thing. Here's one. I don't have it drawn here, but what I like to call a shoulder point. So just as a visual aid, let's look at my shoulder here, right? So in kind of this direction, notice it's kind of like it's an inflection point, right? But in that direction, sort of front back, it's like it's a maximum. That's weird, right? It's not a saddle. It's different. It's just yet another sort of weirdo little thing, and I always think it's fun to mention this thing called a monkey saddle, and I've already done the image search here, and this is a picture of a monkey saddle. Now, first of all, let's try to understand what's going on in this picture, and you can see it's kind of in this direction, it's kind of curving upward, and then also, though, in this direction, it's kind of curving upward, and then also in that direction, it's kind of curving upward, and then, but now there's kind of a downward sort of slope where you kind of want to ski kind of downward in that direction, but there's also a downward slope that way, and there's also a downward slope kind of coming toward us. So it's not like a regular saddle where there's sort of 2 ups and 2 downs, right? This has 3 ups and 3 downs, you might say. And they call it a monkey saddle because the monkey needs 3 down slopes, 1 for each leg, 1 for his tail. Tell me that isn't adorable, right? And then on the Google search, somebody actually drew a monkey sitting happily in his monkey saddle. It's pretty funny. And then so if you scroll down far enough, you can find somebody actually put a little monkey on a dog. Right? It's got nothing to do with the math, but still it's kind of funny, right? So you can scroll down and look for that. Okay, let's see here. Okay, so moving along, back to here. Okay, so let's do one. We're going to find all the critical points for this function right here. Now notice this function is defined everywhere. So the domain is R2. Every point in R2 is interior. There is no boundary for R2. Right? So, did we find any boundary critical points? Nope, there aren't any. Okay, fine. Notice as well, this is a polynomial, and every polynomial is differentiable everywhere. That means there are no points that fail the differentiability condition. So, we didn't get any critical points from that condition either. Notice I'm just going down the list here. Right? We've checked -1, we've checked -2, and now we've got to check -3. I've got to look here for points where the gradient is 0. So I compute the gradient, set it equal to 0, now I've got an algebra problem. Notice I'm looking for points where that's equal to 0 and that is also equal to 0. And conveniently, the second condition obviously means y is 0. The first condition obviously means x has to be plus or minus 1. And so we found 2 critical points. Both from the third and none from the first 2 conditions. Okay. How we doing? Is everybody happy? All right. Now, sometimes the algebra is not that clean, and if that's the case, then you got to deal with it. There are a lot of high schools out there where instructors, teachers, whatever they call them, have told students, don't worry about this kind of stuff. Oh my gosh, that's outrageous. Of course you have to consider all of the actual cases, right? What are we doing here if we're not actually solving the problem? So anyway, heads up for this kind of stuff. It will sneak up on you, partly because some of you at least have been misled in the past by teachers. So so let's suppose this were the scenario and this were the gradient, and we were setting that gradient equal to 0. The very first thing you notice is that x squared has to equal to y squared, and a lot of students have been told outrageously that means that x is equal to y. Right? Or that, that's all you have to worry about. So this is not true. Oh my gosh. There's, of course, 2 perfectly reasonable, equally likely even, you might say, possibilities. It could be x is y, or it could be x is negative y. Either one of these could be. Everybody good with that? So watch out for this kind of thing. By the way, partly because of stuff like this, I put together a video. It's on the Miscellaneous Topics playlist, along with a bunch of other videos that I think y'all may find useful. This one's called Algebraic Pitfalls. And this and other kinds of things where either high schools have told you false statements or they've swept little issues under the rug. Right? They've made a trail that walks around the landmines and not mentioned that they're walking around the landmines, and now you need to know where the landmines are. Right? So various little issues of algebra that a lot of students mess up because they never got addressed well in high school. So I encourage you to take a look at that if you have any concerns about any possibilities. If you're not so good with inequalities, or if you always get confused with absolute values, whatever, give that video a look. Okay, so let's think about our cases. I'll start with case 1. Here we go. Case 1, what if x is equal to y? Well, if that's the case, right, then that expression that needs to equal to 0 turns into this, which gives you values of y. And of course, if you have those values of y, and all of this was on the assumption that x equals to y, then that gives us these 2 critical points. Is that cool? Now, the one, again, that a lot of students, normally would just straight up miss, we got to consider the possibility that x could be negative y. And if that happens, you plug that in, that turns into this, which means now that expression is 0. Again, easy to solve, a little bit of algebra. You get these values of y, but now remember, those values of y came from assuming x was negative y. So those give these critical points, and note in particular, this one here, you would have missed, right? That is conspicuously absent from the list that we found by looking at the first case. And we reproduced 0, 0. Okay, fine. Yeah, whatever. That's harmless, right? But you skip cases, you're going to miss critical points. Okay. All right. Just a point of order. Y'all have heard me say this a lot. This being the last lecture day, this may be the last time you hear me say this. I don't know, maybe not. But it's not about the answer, right? So had the function been maximized at this point, right, then, the fact that you might have missed one of the critical points, again, you could take the point of view, well, we were looking for the absolute max and I did find it. Yes, you did find it, but your reasoning doesn't hold water. You didn't consider all the possibilities, right? If you're looking for the tallest person on Duke campus, but you only measure the heights of like 3/4 of the people, you can't conclude that you found the tallest person on Duke campus. There's a whole bunch of people you didn't even look at. The reasoning becomes invalid. So again, it's about the reasoning, not the answer, and possibly the last time you'll hear me say that. We'll see. Day ain't over yet. All right. So anyway, make sure to consider cases. All right. Okay, so once you've found critical points, how do we classify them? How do I look at a critical point where the whole idea of a critical point is I don't know what's going on there. How do I decide if it might be a local max or a local min? How do you tell the difference? Again, let's look back at single variable. In single variable, different takes that you can take, I suppose. But I'm going to use the Taylor polynomial, second order Taylor polynomial. And the big idea then is, well, if you're looking at a critical point, then the derivative is 0. That means this whole term kind of disappears. And so how the function deviates from that value at the point A is entirely controlled by this expression. And if you look at this expression, you'll notice pretty quickly 1/2 is positive, and this is a square, so that's positive. And so whether this second order term is positive or negative is entirely up to looking at that second derivative. Whether that second derivative at the point A, whether that's positive or negative, completely controls the behavior of this function near A. And if it's positive, then we have a bunch of positive second order terms, which means it's curving upward, which means you're looking at a minimum, local minimum. Right? Everybody that kind of familiar, right? Okay, so what we're going to steal from this is that looking at the second order term is the way we tell. Right? And so our second order term here was easy to understand because it's a product of scalars. There's just not that much to it. Right? But our second order term here is not. I see vectors and matrices and dot products, and this is not so easy to deal with. So thankfully, y'all had a course in linear algebra, and you remember quadratic forms, and you remember positive definite, negative definite, all that business. So no surprise. Just like we just saw, if it's positive definite, that means all the nearby values are larger, and that means you're looking at a local min. Right? So this is what we need, right? We need to understand whether this quadratic form is positive definite, negative definite, or indefinite. And I know y'all have techniques for that. Good news, we're going to have an even better technique here. And the reason why is because the derivatives that we're looking at, and by the way, we're going to restrict our attention just to functions of two variables. Only two variables. Things get a little weirder, a little bit more clunky, a little bit more inconvenient if there's more than two variables. The formulas are in the book if you need them. But for 219, we're just going to focus on two variables. Anyway, here's the big idea. The matrix. Right, looking at our quadratic form, the matrix in question here, being a Hessian matrix, being made up of a bunch of second partials. Second partials, doesn't matter which order you do the second partials, this matrix is symmetric. If it's symmetric, that means it's diagonalizable. If it's diagonalizable, you can diagonalize it in various conclusions you can draw. And this is a some checkpoints along a line of a significant line of linear algebra reasoning that we're not going to bother with. But if you're curious, diagonalize, do a change of basis, you're going to end up with formulas that look kind of like this, and then you can kind of put it together. But you don't have to. That's just if you're curious. And anyway, here's the punchline. The second derivative test. Again, it's quite a bit weirder than the single variable second derivative test. It's the nature of the beast. And here it is. Step 1, write down your Hessian matrix. Step 2, compute the determinant of that Hessian matrix at the point you're interested in. Step 3, consider these 3 different possibilities. Write that determinant, the Hessian determinant, you might call it. Could be positive, could be negative, could be 0. And that tells you which one of these roads to go down. And conveniently, 2 of these roads are really short roads. If your determinant 0, you lose. The test fails. The test tells us nothing. We conclude nothing. It's just sometimes the test doesn't work. The ditto in single variable. If your determinant is negative, it's a saddle point of some sort. Might be a monkey saddle, might be a regular saddle. It's not a max or a min. It's some sort of, could be a shoulder point, right? Something weird. Okay. The third possibility requires a little bit more work. If you have a positive determinant, then you then furthermore have to look at the top left element of the Hessian matrix. You've got to look at your XX second partial. And what's nice about this is this business right here really does look a lot like the single variable second derivative test. Positive means min, negative means max. But very importantly, notice that this only has any relevance. Only has relevance if, in fact, your Hessian determinant is positive. So you can't just use this by itself. It just straight up does not work. Okay. Everybody on board? Now, where does this come from? Well, again, a bunch of linear algebra, and if we had an extra, if we had, after spending any extra time on more important things, if we still had an extra half hour to kill, then I would go through and show you how that works. But we don't have that half hour, and it's also not the top priority of how to spend an extra half hour. So anyway, here's the test in action. Let me get it all on the screen at the same time here. And in fact, why don't I do this so we can see better? So we have previously looked at this function. We found the critical points, at which point we kind of threw up our hands and said, well, these are points where we don't know what's going on, and oh well, right, we just kind of left it. So now let's actually go through and try to identify what's going on there. So again, step 1, you got to compute your Hessian matrix. So I've got to take this function, compute the second partials, and there's the formulas for the second partials. Next, I've got to take the determinant of that Hessian matrix. So okay, here you go. There's that Hessian determinant. And then I've got to see now, for each one of the points that I'm interested in, I've got to see, is that Hessian determinant positive, negative, or 0? Okay, well, let's start with that point. Plug that in. Hessian determinant's negative. Negative means saddle. Everybody good? Okay. All right. Let's see here. Now we look at this point. 1, 0. Again, we got to play the game. We got to plug in, see what is that Hessian determinant. And for that point, that Hessian determinant is positive. That tells us that the game's not over. That tells us we've got a further look now at fxx. Okay, so that's the top left element here. And again, plugging in the point in question, x is 1, y is 0. And so our fxx is positive, and positive means local min. Okay. All right, so that you get the hang of it. Okay, so make sure to know these rules. It's one of these things you just have to memorize. There's not a lot in this course, by the way, that is just straight up, just trust me on the formula and memorize it. There's a couple of things that are just, just trust me on the formula and memorize. Like the formula for curl, right? I didn't show you why that's true. I don't think we really have time to justify. But this is another one that you just have to take on faith. Of course, most of what we do in this course is stuff that we've talked about the reasons for, and so that's not so much memorization as understanding. So the collection of things that you have to just rote memorize is pretty short, but this is on that list. Okay. All right. Moving along. How are we doing on time? We're fine. Okay. So this business about global extrema, we're not going to spend much time on this. This is another topic that can be as time-consuming as you want it to be. And I do want to point out that just because you found a critical point, even if you found a local max, that doesn't mean that it's the absolute max. And it furthermore doesn't even mean that the absolute max that you're looking for even exists. Right? So here's a couple of scenarios, right? Easy to look at scenarios where there is no maximum value of the function. Right? So that can happen. So don't think of finding absolute maxes as being just a process where you find this thing that of course exists. No, it may or may not exist at all. And being on the hunt for something, not knowing even if it exists, is unsettling. Right. So here's a wonderful theorem, really nice theorem that will allow you to conclude under certain conditions that there is a global max of a function. And the three conditions are as follows. The domain is closed, namely it contains its boundary. Notice that was kind of the issue here. That's ensuring that this story in the left picture there doesn't happen. If the set is bounded, in other words, if you can put it inside of a box or a ball, whatever, that would ensure that this little story here doesn't happen, right? And then if your function is known to be continuous, well, that would ensure that this little scenario doesn't happen. And it turns out these are the three things that can in fact go wrong. And if you have a function defined on a defined on a closed and bounded domain, otherwise known as a compact domain, by the way, a little lingo. And if your if your function in question is continuous, if these three things happen, there is a global max. It's just a question of finding it. Okay. All right. Now, something we've kind of been sweeping under the rug, we haven't really dealt with, is how to deal with boundary points. Right? We know that if you have a boundary point, then we have to call it a critical point. Our tools don't allow us. The tools that we have so far don't allow us to eliminate this point being on the boundary as a possible maximum. Maybe it is, maybe it isn't. Our simple-minded, the function is increasing in some direction, argument fails. Right? So how do we deal with these boundary points? And there's tempting to say, just check them. Right? So for example, if you go back to the single variable case, boundary points, well, there's only 2 of them. Just check them. That's how single variable calculus classes deal with the boundary. There's just 2 points. Just check them. Well, no such luck for us. No such luck for us. We have infinitely many boundary points. I can't just check them. I don't have that kind of time. So, we're going to need something smarter than that. One thing you can do, and I'm going to let you all read the details on this because this is ultimately not the best way to go. This is what one might call the most obvious way to go. But ultimately, there's a much better, much slicker, much more powerful method than this. Anyway, the big idea is to say, look, the top part of this disk, that's half of my boundary. On the top part of the disk, y is a function of x. That means that for those values, I can rewrite my function as, well, frankly, a single variable function of just x. And if you want to find critical points of a single variable function, you take the derivative, set it equal to 0. Right? So that's the big idea. And don't forget to check your endpoints. Right? So anyway, that's the big idea there, and it's pretty natural thing to try. But notice, of course, you do have to do that for each piece. The top edge has a different formula than the bottom edge. Right? On the top edge, y is the positive square root. On the bottom edge, y is the negative square root. You get totally different algebra. And so you got to go through, and you can see it's a little clunky. It's not the worst thing in the world, but it's a little clunky, and wouldn't it be nice if there's a better method? So I'm going to skip to the better method. And if y'all want to wade through algebra, you're welcome to. Okay. All right, so this better method is called Lagrange multipliers. Really, really clever idea. In fact, this applies even more broadly than boundaries. This applies in any situation where you want to maximize a function, maximize or minimize, whatever, but with an algebraic constraint. So, for example, maybe I want to maximize this function. In this case, I want to minimize that function there. I'm trying to find closest to the origin, right? So I want to make this function here as small as possible. But the obvious answer of, hey, look at the origin, right? Obviously, that function I'm trying to make as small as possible is never negative, and it's 0 only once, and so that's the minimum, right? But it's not allowed because I'm looking only at points that satisfy this constraint. 0 is not allowed. 0 doesn't satisfy that constraint. I'm only allowed to look on this wacky curve, whatever that is, and only on that curve finding the point closest to the origin becomes a much harder problem. Everybody see what I mean? Okay. So the method on this requires that we write this as it is as a level set, that we identify then, let's see here, I guess I have to use another color. We identify the function whose level set I'm looking at, and we call that our constraint function. So very important that, but there's a constraint equation, right? That's the equation that you're given. The constraint function relates to the constraint equation by the equation is a level set of the function. And the fact that it has a level set is going to be really, really important. Okay. All right. So, for example, if your constraint equation comes to you in a different form, For example, maybe your constraint comes to you as x squared plus y squared equals 3xy plus 4. Right? Don't make the mistake of thinking that the constraint function is this. It's not. And likewise, equally ridiculous, it's not that either. You've got to rewrite what you're given as a level set. Got to be a level set, and then whatever's left over, whatever function you're looking at a level set of, that is your constraint function. Everybody see what I'm doing there? Okay. Really, really important. Okay, so what a weird question. Wanting to maximize or minimize functions subject to a constraint. Why would we be interested in this? So I have a couple of examples. Now these are I'm just going to throw these out real quick here, right? But here's a very natural engineering question. Different ways to the sort of different versions of this question. But if you're working for some big company that does a lot of shipping, maybe I won't say any names, this is a pretty important question. How to make the biggest box you can, given the limited amount of cardboard. Cardboard's not free, right? Multiply by 10 billion and save a couple of pennies. That's a big deal, right? So this is a constrained optimization problem because volume is what I want to make as big as possible, right? And area is what is fixed. So I've got a constraint represented by the constraint function called area, and then my objective function I want to maximize is volume. Okay, here's one that's from more from economics. Let's suppose you're starting a small business and you've got a limited budget. Okay, well, limited budget. Limited means that is what is fixed. So whatever the formula is for how much money you're spending on various different things, that has to be fixed. That is your constraint function. And of course, what do we want to maximize? Depends, right? Sometimes you want to maximize profit. Sometimes you want to maximize revenue. Sometimes you want to minimize risk. Sometimes you want to maximize productivity. Various different things. That is your objective function. Okay. All right, so how to do it. Here's the big idea. Now, again, notice the layout on the page. Very similar layout to how we addressed this in the single variable and in the previous the unconstrained multivariable case. And here you go. By the way, let's talk about the picture first. Here's my constraint set. Notice the constraint set is written as a level set. Here's why it matters that be a level set, because I know if the set I'm looking at is a level set, then the gradient of that function is always perpendicular to that constraint set. Right? Flashback to chapter 2. All right. Okay, so that's handy. Now, having noticed that, let's look at the following three conditions. What would happen if these three conditions hold? If I have a couple of differentiable functions, in other words, if I'm allowed to use derivatives in the usual way, we need that just so that we have tools accessible to us, right? What happens if the gradient is non-zero? The constraint gradient is non-zero. Well, if the constraint gradient is non-zero, that means it's actually pointing in a direction. And we know that it has to be pointing in the direction perpendicular to the surface. And so that means that all vectors perpendicular to the surface are just multiples of that constraint gradient. And now imagine that the objective gradient is pointing not perpendicular to the surface. But what I have in light blue there is all of the vectors that are perpendicular to the surface. So if it's not, then it is not one of those blue vectors. Is that cool? Okay. All right. Okay, so in this case, what can I conclude? Well, all of these conditions, this picture being as I have it drawn here, I think the function's increasing as I go. Oh, wait a second. I'm not allowed to go in that direction, am I? That's the twist. That's tempting to say, just go in the direction that the function's increasing the fastest. But you can't. But what you can do is you can go in the direction of its projection. You can look at its projection in the tangent plane there. That's a direction that you can go. And as you go in that direction, the function is increasing. And so that point that we were looking at here, this point A, couldn't possibly be the maximizer. Check it out. The function's increasing as I go to the right in this case. Everybody happy? Okay, so we found, again, a tool that will eliminate most of the points in the domain. What we're going to be interested in are the points where those conditions fail. These are the points that we can't eliminate. These are then the three different conditions that I have to check if I want to find critical points. So that's what we're going to do here. We're going to look at where does either function fail to be differentiable, where is our constraint gradient 0, and where does this thing happen? Where is the objective gradient a multiple of the constraint gradient? So just for lingo purposes, by the way, this is what I call the differentiability condition, natural terminology, for reasons that are not clear in this context, but that makes sense in another context. We call this the degeneracy condition. There's, again, really good reason for this. That's called the degeneracy condition. And this is called the Lagrange condition. This is, again, it's the one where, frankly, most of the time, this is the one that's going to lead to the critical points that you're actually looking for. Most of the time. Not always. Definitely not always. But, most of the time. Okay. All right, so here we go. Let's do it. Let's look for how would I find the highest point on the surface with that equation. So that equation right there, some surface, some weird surface. I think this is a rotated ellipsoid, if I had to guess. And anyway, so this weird sort of angled rotated ellipsoid, what point is the highest on that surface? So highest means that I want to maximize, I want to maximize z. So z is my objective function. I have here already written conveniently as a level set that my constraint gives me this as my constraint function. Everybody with me? Got an objective function, I got a constraint function, and now we just go down the list and start checking conditions. So let's see here. Do any of these functions ever fail to be differentiable? Nope. By the way, that's an easy one. If you see a question like this on the exam, don't forget to write down that your two functions are both differentiable. It's usually eyeball glance obvious that they are. And if you write that down, you have successfully checked one of the conditions, and that alone, depending on the grader, could be worth a couple points or something. So easy. Don't leave the points on the table, right? Get those points. Yeah. All right. So again, don't fall for the mistaken reasoning that only the answer matters, and I don't think I can at a glance tell that that's not going to give me any critical points. That's not going to get me to the answer, and therefore I don't care about it. So wrong, right? That's philosophically just wrong. So the point isn't whether it leads to the answer. The point is whether it is a necessary part of the reasoning. Okay, so there it is. I did say it again. Anyway, make sure to acknowledge necessary parts of the reasoning. Okay, next question. Where is the constraint gradient equal to 0? All right, well, we take our constraint function. We look at its gradient, which, by the way, you can rewrite like this. Right, a little bit of algebra. Want to know where that's equal to 0? Flashbacks to linear algebra class. Right, homogeneous system of equations, square, matrix. Various different ways you could do it. You could row reduce, blah, blah, blah. The easy foot in the door on this is to notice that this matrix is non-singular, and non-singular matrices pivot in every row, pivot in every column, various different takes, always unique solutions, blah, blah, blah. Anyway, the nice punchline from these observations is that this is the only point that satisfies that degeneracy equation. And it's tempting to call that a critical point. Remember, though, critical points are points in the domain that satisfy certain, whatever conditions. This point's not in the domain. This point doesn't satisfy our constraint. So the fact that it came up in the algebra is just kind of irrelevant, random. Who cares? I don't need to eliminate this point. This point was not a contender in the first place. So it's not a critical point. That makes sense? Okay. All right. Okay, so 0 for 2. We don't have any differentiability critical points. We don't have any degeneracy critical points. So we write down our Lagrange condition. By the way, as we just noted, we only care about points that satisfy the constraint. So altogether, here's the algebra that we need to do. We need to figure out how to solve that algebra. It's 4 equations with 4 unknowns. And every single one of these is different from every single other one. The methods, you got to kind of look for your foot in the door, catch as catch can, do your best. There are certain things that happen consistently that are convenient. What you're going to notice here is that it's pretty easy to persuade yourself that these two things need to be 0. And if so, then I can solve for x and y in terms of z. I can then take this information and plug it into there, which I can then solve for z. And once you know z, then you know your resulting x and y. So that's not a rare story. This breakdown happens sometimes. Anyway, be on the lookout for this kind of thing. Now, does everybody see how this algebra went? And then real quick, I just want to point out I did commit a little crime here. Did it on purpose. I like to catch people off guard. This first step, as I presented it, I just wrote this down. Didn't really follow. Because I looked at these equations, and I just casually, we'll just cancel the lambdas. You can't cancel stuff unless you know it's not 0. Right? It's just a thing, right? I mean, if 0 is equal to 0 times x, and if 0 is equal to 0 times y, can I conclude that x and y are equal? No. You just can't. It's just wrong. All right? I mean, I feel like this was glaringly absent from my high school algebra classes. But it just doesn't work. So anyway, you got to establish before you get excited about the algebra, and and like I did here, before I take this and come down here, et cetera, et cetera. You got to establish that lambda is in fact non-zero so that you can cancel it. And this is how you establish that it's non-zero. You look at this equation. If lambda were 0, that equation couldn't possibly work. So equation C there, in fact, as I needed, establishes that lambda is not 0, and then and only then can you cancel those lambdas. So watch out for these little algebraic pitfalls, and now I'm going to leave it to y'all to look at the remaining examples here. There's good little algebraic pitfalls to watch out for in these remaining 2 examples. I will publish a I will publish a recording that I have from last semester, I think it was, talking about these last examples to give you a reference. And again, just be careful with that algebra. Don't forget to check cases. And okay, all right, we're all done. Congratulations, y'all, and see you on Monday. Good luck with your studying, exam 3 and all that. Okay. Whoops.